For the last decade, electric vehicles were marketed as the ultimate solution to climate change. Skip the gas pump and drive away with zero emissions. But this diagram shows the thermodynamic reality of driving an EV in cold weather. Internal combustion engines produce abundant waste heat to warm the passenger cabin. EVs don't. When temperatures drop below freezing, energy from the battery pack drains away from the drivetrain and is actively rerouted to heat the interior, dropping the vehicle's driving range by up to 40%. Even in perfect weather, EVs carry a hidden mechanical burden: their weight. Lithium-ion battery packs make electric vehicles roughly 20% to 30% heavier than their gas-powered equivalents. That excess mass, combined with the instant torque of an electric motor, forces EV tires to wear out 20% faster. This rapid tire degradation creates a new non-exhaust emissions crisis. As those heavier tires grind against the asphalt, they shed massive amounts of toxic microplastics and particulate matter directly into urban air and soil. That heavy, highly sensitive battery pack also sits exposed at the bottom of the chassis. Minor undercarriage damage that would mean a quick repair for a standard car can compromise the internal cells of an EV battery. Because replacing the pack often costs half the value of the entire car, insurance companies are increasingly forced to total the vehicle, driving up insurance premiums for every EV owner on the road. High insurance costs, range anxiety, and rapid mechanical wear are symptoms of a highly volatile, unperfected technology trying to scale before it's ready. The extreme sensitivity of these battery packs presents a specific physical danger: a cascading, self-sustaining chemical reaction known as thermal runaway. This animation shows how thermal runaway works. When a cell overheats, the chemical decomposition of its cathode releases oxygen gas internally. The cell generates its own oxygen, feeding an internal flame. Because the fire supplies its own oxygen, traditional firefighting fails. Fire-smothering foam washes completely over the exterior, while the chemical fire continues raging inside the casing. Emergency responders are forced to resort to extreme measures. Suppressing a single EV battery fire requires flooding the exterior with over 10,000 liters of water just to cool the pack down. Often, fire departments must crane the vehicle into a specialized containment unit and submerge it entirely for weeks to prevent the battery from reigniting. When the reaction finally concludes, it leaves behind skeletal frames and toxic runoff. These driveway frustrations and localized fire hazards are the visible symptoms of the technology. To measure the true cost of an electric vehicle, we have to look past the finished product, crack open the battery pack, and trace its components upstream. This comparative bar chart shows the carbon debt every EV carries at birth. Producing the battery pack is so resource-intensive that manufacturing an electric vehicle generates roughly 46% of its lifetime emissions, creating a massive initial deficit compared to building a traditional gas-powered car. That massive footprint begins with extraction. High-energy density batteries rely on cobalt to stabilize their chemical structures. Today, the Democratic Republic of Congo holds roughly 70% of the world's cobalt reserves. Up to 30% of the cobalt exported from the DRC is pulled from the ground by the informal mining sector, an unregulated system relying on an estimated 40,000 child laborers who sift toxic dust by hand, suffering documented respiratory disease and measurable DNA damage. Automotive and tech giants frequently claim to source their minerals strictly from regulated industrial mines, but the supply chain is highly fragmented. Artisanally mined cobalt is routinely sold to middlemen and blended with industrial supplies at local processing depots, making it impossible to separate the clean material from the tainted. The clean energy stored in Western driveways is heavily subsidized by the untraceable exploitation of laborers in the DRC. Cobalt isn't the only bottleneck. The global rush for battery-grade nickel has shifted the epicenter of the industry to the forested islands of Halmahera, Indonesia. Here, the landscape is being stripped to access low-grade laterite ore, pushing brown sediment-filled water directly into local fishing grounds. Because Indonesia's laterite ore is extremely low-grade, it cannot be used in batteries without aggressive refining. Processing this ore requires high-pressure acid leaching, a method that uses extreme heat, pressure, and concentrated sulfuric acid to extract the nickel. This scale visualizes the mathematical reality of acid leaching. To produce a single ton of battery-grade nickel, the process leaves behind 133 tons of highly corrosive, toxic waste, known as tailings. That corrosive slurry has to go somewhere. It ends up in massive land-based tailings ponds, where gray and orange mineral runoff seeps into the soil, permanently contaminating the local groundwater aquifers with heavy metals. The modern battery supply chain relies on a chemical processing method that mathematically prevents ecological preservation. Then there is the energy required to run these operations. Indonesia's massive green industrial smelting parks are entirely cut off from the public grid. Instead, they are powered by captive, on-site coal-fired power plants. When fully operational, the power network serving just one of these industrial zones will burn more coal annually than the entire nations of Spain or Brazil, offsetting the downstream climate benefits of the electric vehicles they supply. To secure the physical footprint required for this industrial build-out, mining companies employ coercive acquisition tactics. Indigenous farmers who refuse to sell their ancestral lands face police intimidation, and properties are frequently excavated after locals are offered compensation of just pennies per square meter. When communities organize to block the mining operations, the Indonesian government weaponizes the law. Under Article 162 of their mining regulations, anyone who hinders the activities of permit holders faces imprisonment and massive fines. Deep in the supply chain, the electric vehicle industry is actively replicating the most abusive, climate-intensive, and corrupt practices of the fossil fuel era it promises to replace. We are currently trading localized tailpipe emissions in wealthy urban centers for systemic environmental destruction in the global south. The industry points to battery recycling as the eventual solution. But today, standard pyrometallurgical recycling literally incinerates the battery pack. The high-temperature smelting process separates heavy metals, like cobalt and nickel, but it completely burns up the lithium and releases large amounts of greenhouse gases. Advanced methods, like direct recycling, aim to cleanly extract and reuse the intact crystal structures of the cathode. While promising, this technology is stuck in research and development. It cannot scale fast enough to meet the millions of tons of battery waste expected by the end of the decade. The transition to electric transportation is a necessary goal. The engineering inside the cars is brilliant, but the execution of the global rollout is severely compromised by corporate greed, rapid scaling, and a lack of oversight. True sustainability requires transparent, audited supply chains and strictly regulated recycling infrastructure. Until the automotive industry confronts these upstream realities, the electric vehicle revolution is simply shifting the damage out of sight.